Now we know how to calculate the pH of a buffer solution. Really simple, we typically just use that Henderson-Hasselbalch equation. Now what we want to do is be able to determine the pH after I've added a strong acid or base. The whole purpose of buffer solutions is that they're able to resist pH changes when any acid or base is added. Now that's not to say the pH doesn't change, it's just that it doesn't change by very much. So the buffer just keeps it within the same general range. However, it does change the pH when we add that additional acid or base, and we want to be able to calculate what the pH is before an addition and after an addition. So calculating a pH change involves two basic steps. First of all, we have to do a stoichiometry calculation. When we add an acid or base, it uses up some of my buffer, and I need to figure out how much it uses up. Second part is a pH calculation. I need to see what I have after I've done my stoichiometry calculation. If I still have a buffer, I can just plug it back into that Henderson-Hasselbalch equation. But sometimes I add so much strong acid or base that I actually use up my buffer, and then I just have a bunch of strong acid or base left. Fortunately, we know how to get the pH of a strong acid or base, so that shouldn't be a problem. So let's look at an example of one of these pH change questions. A 2-liter buffer solution is 0.1 molar in acetic acid and 0.1 molar in sodium acetate. Calculate the new pH after 0.010 moles of solid sodium hydroxide is added. Now, the first thing I like to do is just look at my buffer and decide who's my acid and who's my base. I want to make sure I don't mix these up. So this one's pretty simple. I see, okay, I have acetic acid up here. It has a Ka next to it. So my acid must be that 0.100 molar acetic acid. That means my base must be the sodium acetate here. Now, we're always going to have in that second piece, in our buffer, we always have an acid plus a salt or a base plus a salt. And so this here is my salt, sodium acetate, and it's always going to have one neutral ion we don't care about. So in this case, I can see that it's going to be the sodium. If I can't see that immediately, what I can do is once I figure out what my first piece is, whether it's an acid or base, I can write an equation of that guy reacting with water. So I have acetic acid plus water. I know that this is my acid, so he's going to donate and produce a C2H3O2 ion and my H3O plus. So I can see that this is going to be my acid and this is going to be my conjugate base. So when I look at what I was provided with, the sodium acetate, it's really just that acetate ion part I care about. The sodium is a neutral ion, so he really doesn't do anything. So my conjugate base here is my 0.1 molar C2H3O2 minus that acetate ion. So once I've identified my acid and my base in my buffer, now I can think about, okay, who is this addition going to react with? So acids and bases always react with each other. So when I put something in my buffer, it's only going to react with one piece of my buffer. And I need to figure out if what I'm adding is an acid or a base, and then pair him up with the correct piece of my buffer. So sodium hydroxide, we should be able to recognize that as a strong base. So he is going to react with my acid. Same thing here, just like with the sodium acetate, with the sodium hydroxide, I really don't care about that sodium piece. That strong base I can just think about as being OH minus. OH minus is the part of a base we really care about, so I'm just going to drop the sodium since he doesn't do anything. And I have 0.010 moles of that. So this part just helps me identify the pieces of my buffer and who is going to react with whom. Now, it doesn't ask me to calculate the initial pH, but I think it's useful so we can figure out where the pH is going to start, and then we can see where my pH ends up after I add that sodium hydroxide. So if I want to calculate my initial pH, I'm going to use that Henderson-Hasselbalch. So the pKa is the negative log of my Ka, which was provided up here, 1.8 times 10 to the negative 5. And then the log of my base over my acid, so I have 0.1 molar of each. And if I calculate that, I see that my initial pH was a 4.74. Again, it didn't ask me for that, but it's an easy little calculation to do to see where I start with, because then I can think about if my ultimate answer makes sense. I'm adding some sodium hydroxide, so I would expect my pH after this addition to be a little higher than 4.74. So let's see if that's the case. So now let's start actually working the math on this problem. So we've established who my acid and base are. So now what I need to do is write a reaction between that acidic and basic component, and then I can start doing my stoichiometry. So I initially had my acetic acid, and I added my sodium hydroxide to it. Acid-base reactions go to completion, so I'm just going to draw my forward arrow. Just like normal, my acid is going to donate to my base. So I'm going to end up with the C2H3O2 minus, and then we're going to produce some water. So in order to do stoichiometry, I always need to have my table ready, or I'm sorry, my balanced equation ready to go. So now that I have that, I'm going to do the stoichiometry, but I'm going to do it in a sort of easy way, and I'm going to make a table. Not an ice table, but I'm going to make what I call a BARF table. So in BARF table, B stands for the beginning moles you have, A stands for what you added, R stands for the reaction that takes place, and F stands for your final moles. Now, just like in an ice table, if we have water, we don't have to worry about him, so we can just cross him out. So if I go back and think about what I began with 0.1 molar acetic acid and 0.1 molar sodium acetate. I added the sodium hydroxide. I didn't begin with him. So I'm going to take my acetic acid and my sodium acetate and put them into my beginning. Now notice also B stands for beginning moles. And so I can't just plug in the concentration, I need to plug in the actual moles that I have. But it's a really easy conversion. So to get moles, you just do your molarity times your liters. So I had 2 liters, and it was times 0.1 molar. So if I do the math on that, I'm going to end up with 0.2 moles. Same thing over here. I had still 2 liters of solution, and it's 0.1 molar. So that means I'm going to start out with 0.2 moles of that acetate ion. And I don't start out with any of my hydroxide. I added that. So for my add, I didn't add any buffer. I added hydroxide, and I added 0.010 moles of that. Now what I'm going to do is look at these first 2 columns right here, and I'm going to think about who I have less of. So I'm reacting my acetic acid and my hydroxide, but I am going to run out of one of them before the other. We should remember back to limiting reactants. So all I have to do is compare these 2 numbers and see who do I have less of. So I obviously have less of the 0.010, and so what I'm going to do is I'm going to react that much. So I'm going to use up that much on the reactant side, which means I'm going to produce that much on the product side. Pretty similar to our ice table. Now when we do this, we see we've used up all of the hydroxide, but we still have 0.190 left of the acetic acid, and we made some more of the acetate ion. I have 0.210 of that. So now what I want to do is I want to look and see what I have left. Sodium hydroxide, that was my strong base. I don't have any of that left. Acetic acid, that was my acid in my buffer. He's a weak acid. And then I had some of his conjugate base. So I have 0 strong base left, but I have some weak acid and I have a conjugate base, which means what I have left is a buffer. And if I have a buffer, I have a really easy way to get his pH. I just use Henderson-Hasselbalch. So I'm just going to plug this back into my Henderson-Hasselbalch. So it's still going to be the pKa, which is the negative log of my Ka, 1.8. Oops, that's positive right there. Let's go back so we don't get confused. It's a negative log of my Ka, which is 1.8 times 10 to the negative 5, plus the log of my base over my acid. Now notice we have moles in my table, but good news is for HH, for my Henderson-Hasselbalch, I can just plug in moles. I don't have to turn it back into a concentration. So I'm just going to plug in my base on top, 0.210, and my acid on bottom, 0.190. It's a 9 there. And then I plug that guy into my calculator, and I get 4.78. Now we can go back to that initial pH we calculated and see how it compares. So initially, before we added the sodium hydroxide, my pH was 4.74. After I add the sodium hydroxide, my pH goes up to 4.78. So we see it increased just a little bit. It went up, which makes sense because we added base, but it didn't go up significantly because the buffers try to prevent that. That's it. So we can see that our answer makes sense, and we are done. All right, that's example 1. I want to show you a very, very similar example down here. So now I have the same buffer system, a 2-liter buffer system that's 0.1 molar in acetic acid and 0.1 molar in sodium acetate. Only difference here is I'm adding a bunch more sodium hydroxide. I'm adding 0.3 moles of sodium hydroxide instead. Now normally I would start this from scratch, but we've already done this work. So just to remind us, up here, this was just establishing who my acid and base are, and that's the same. I still have 0.1 molar of an acid, 0.1 molar of a base. I can still establish that by writing this equation here, and I can calculate my pH. So I don't need to do all that work again. I'm still going to react the acid, my acetic acid, with sodium hydroxide, which is what I'm adding. So I can go ahead and I can really start here. Again, just because we already basically did that first part of the problem where we established who my acid and base are. So I'll make a little note just so I can remind myself. This guy's my acid. This guy is my conjugate base. I'm adding a strong base, so it's my acid and strong base that are going to react together. So I'll write an equation for that. Again, we always got to write our equation. And again, I'm going to represent my strong base as just OH minus, because that's all I need. The sodium doesn't do anything. My acid is going to donate, so I end up with C2H3O2 minus, and I produce some water. I got to do my stoichiometry again, so I'm going to make my BARF table. Don't have to worry about my water. Again, I need to have moles. So for these, I start out with liters and concentration, so I'm just going to do a little multiplication. I have 2 liters times 0.1 molar, which means I start out with 0.2 moles. Same thing over here, 2 liters times 0.1 molar will give me 0.2 moles. And I didn't start with any sodium hydroxide, so I didn't begin with any there. I don't add any to my buffer. I add this hydroxide, and I add 0.3 moles of it. Now again, I look at my reactants and see who I have less of. This time, I have less of the acetic acid. I have 0.2 there, 0.3 of the sodium hydroxide. So I always pick the smaller number and react. That's my limiting reagent. So I'm going to react 0.2 moles, which means I'm going to produce 0.2 moles over here. So this time I end up with 0 of the acetic acid. I still have 0.1 molar of this, and I end up with 0.1 moles of the hydroxide, and I end up with 0.4 moles of the acetate ion. So again, I'm going to see what I have. Acetic acid was my weak acid, hydroxide was my strong base, and this was my conjugate base. So let's see what we have left. We don't have any weak acid this time. Instead, we have a strong base and a conjugate base. So if I have 2 bases and one's strong and one's weak, and a conjugate base is going to be weak, what I'm going to do is just ignore this piece over here. Between a strong piece and a weak piece, the strong piece is really going to dominate, so I'm really just going to worry about this guy over here. So I'm just going to treat this guy as a strong base. That weak conjugate base is going to do so little that I really don't have to worry about him. So now when I get the pH, I'm just going to worry about this strong base piece. So we have practiced many times how to get the pH of a strong base, but one more thing I need to remember is that this 0.1 here refers to the moles of hydroxide. And anytime we're getting pH, we always dealt with concentration of hydroxide. So what I need to do is turn those moles back into concentration. Good news is pretty simple. So the concentration of hydroxide, I'm going to take those 0.1 moles, I'm going to put them over the total volume that I had, which was the 2 liters of buffer I started with. So I need to turn that back into a concentration. I get 0.0500 molar. And now life is really easy. First, we can get the POH, which is the negative log of that OH minus concentration. And if we plug that into our calculator, we get 1.301. And of course, pH is just 14 minus that POH. So we find that the pH is 12.699. Now, if we compare this to what we had originally, we can see that we had a huge jump. The original pH of this buffer solution was 4.74, but now my pH is 12.699. So we can see that the pH did go up, which we expected because we added base, but now it went up by a lot. So what happened, if we go back to my BARF table, is we see that I actually used up all of my buffer. I ended up with 0 of 1/2 of my buffer. And if I use up one piece of it, my buffer's gone. So this is called breaking your buffer when you add so much strong acid or strong base that you actually destroy it and use up 1/2 of your buffer. And then you'll see a very large pH change. So, in example 1, we only added a small amount of a strong base, and at the end we still had my buffer left, and that's why we only saw a very small pH change compared to where we started. The second one, we added a very large amount of strong base. We used up all of my weak acid component of the buffer. We broke that buffer, and that's why we saw a very large pH change and a very basic pH at the end, because we just had a bunch of strong base left. So all pH change problems when it comes to buffer look like this. Again, to remind you, the important first step is establish who your acid and base are. Then see if what you've added is an acid or base, and then react them accordingly. If I had added a strong acid, I would need to react him with that conjugate base piece, but because I added a strong base, that's why I reacted him with this acidic piece. So after you write your equation, you can make your BARF table, and then just look and see in that final row what you have left, and that will tell you what to do to move forward.